Hi folks, see you speaking again. We studied all the basic gates. There are only 6 or 7 of them if you add the exclusive NOR. And I thought we could pass to some projects to give them a good use now. But in the meantime, I had a repetitive question. And this was, hey, can you explain better how do you use the breadboards for the projects? So I had to stop it, and today we're going to discuss a bit about the breadboards. Let's start. When you think about a breadboard, it's a kind of prototyping object you use to place components to check if your diagram you found, I don't know, somewhere on the internet, or even if it is from someone you trust, you find out that this diagram is working fine. Or simply maybe you have to do adjustments to the components, either component size, or if it's not the size, the number of components and so on. Because what's coming here is the first step of a prototyping activity, which is continuing with something like this, which is soldering on a prototyping board. If you take a look here, this is exactly like the drawing you have in any software, excepting it's done manually. I don't need this prototype to be replicated in 1,000 or 10,000 spares. For that reason, it's going to remain like this as a prototype. There is no reason to invest money in putting this again in a software, in a Gerber file, to be reprinted to make printed boards. Or if it's going more complicated and the project is bigger, same story. So here there are no extra wires, everything is just fine, exactly like in any software you like, excepting the wiring is soldered by hand. So this would be the second step. I repeat, first step is to check your project right here on a prototyping breadboard, and on this one you can do whatever modifications you need, okay? Because then when you pass here, it's much more difficult than to remove a component from such a project and to replace it in case anything went wrong. This is why you need first the breadboard. And the next step after this, the third one, would be to put all that circuit in a software and to replicate it in the copies if you are a company and you need to make 1,000 or 10,000 copies, okay? Good. Now let's see how these kind of breadboards are organized and what are you doing with them. So basically what you do with them, you place components here and there on this breadboard following different kind of diagrams. Now here is a kind of little trainer. Here is the USB input signal for programming, and when you program all this little board, you have here an extra breadboard, supposedly giving you options to put some external components to check your first ideas about programming. Let's take the number 170. You think it's a big number, 170. That's exactly the number of holes you find here on this little breadboard. It's not much, because you think 170 is a big number, but when you see them here, the room, it's a very small one. And just to compare, to find out what about this number, so 170, this is 270. The breadboard is a bit bigger. Take a look. You only have room for a couple of components, not many, just a couple of them, and then the board is practically filled with parts and you can't do a big deal. So 170 holes, 270 holes. So basically you are going to need a bigger one. So if I'm picking up a more professional programming board, it's coming with a breadboard right in the middle. Here you can put some other components to check if your programming is working fine, okay? So this one here is a typical one, which is called 840 holes. Now, These holes, how are they arranged? Again, 840. This one here is similar. It just doubled. There are two sections. Let's call this one a section, because all the professional breadboards are based on that kind of section. And you can have one section like here. You can have two sections like here, 3, 4, or 5, depending how big the project you intend to do is. So there is no big difference between that section and this one, because this is 840 holes and this is 830. So it's a very minor difference. But this kind of arrangement here is absolutely identical to what you see on my screen. So on the screen, if you take a look, there are the top rows. I'm going on the horizontal, the top rows, which are these ones right here. And as you can see, there are only groups of 5 contacts, but all the holes are related together inside the breadboard from the left to the right side. So they're making a full line. We're going to use, as you can see here, the color, the red. We're going to use as a positive line, so you can pick up, not because you need so many holes. And by the way, here there are 50 holes in the top row and 50 holes in the bottom here. It's not because you need 50 holes for the positive voltage or 50 holes for the negative, which is the blue line. It's just because the manufacturer wants to give you access from any place here on the line to your circuit where you need to draw a wire. Okay? So then all the holes are coming together, the top row, all the holes, and the bottom row, all the holes. And I can show this to you right away, because if we put it right here, and if we just connect 2 pieces of wire, one on the end here, on the top row, and another one here, regardless the length of the wires is not relevant, and we measure here the ohms, okay? Let's put here on, okay, on wrench, like this, to not see too many zeros. So then, I keep one lead here, the other one here, and I have continuity, see? So I have continuity, and I'm gonna move this on the bottom row, like that, and I'm gonna measure again, and I have continuity. And if I put between the 2 rows to check the 2 rows are not related. You can see overload. So overload means what? The resistance is huge, infinite value. It's so big you can't measure it. Why? Because the 2 rows are parallel, they don't touch each other. Similarly, if I move these on any other line, let's say I'm gonna move it on the blue line over here, okay? And I measure again, I should get continuity right away, you see? So it's continuity. All the holes left to right, exactly like here, left to right. It doesn't matter the top or the bottom, are together. So far so good? Now, there is one point though, before we go any further with that. There are some boards, like this one here, we'll have to be careful. You see here there are groups of 5. 5 here, and 5 here, and 5 here, and so on. And you watch the gap between the groups of 5. And the gaps are perfectly equal to each other, excepting here in the middle. So when you see a larger gap, the meaning is this row does not respect the same rule as the one on the screen or the one over here. Because over here, if you compare the two, after 1, 2, 3, 4, 5, this gap here is absolutely the same as the one before or the one after it. So here is a continuous line, not here. So anytime you see in the middle, it can only be in the middle. You see a larger gap, the meaning of that is you have continuity from here to here, but if you want this line to be continued to the end, you have to place a jumper where the gap looks larger. Let's check it, okay? So, if I connect a wire on the top row from here to here, and I'm checking it with my ohmmeter, of course I'm going to find continuity, like this. So continuity, okay? But if I place the white wire right here, anywhere after the first half and I'm trying to measure, I'm going to get overload. So there is no continuity. If I want this line to be continuously going left to right for my positive, let's say, then I'm going to need a kind of jumper to place anywhere between the two to just overpass the larger gap. So if I measure right now, and I'm going to move this one to the very end of the line, I'm going to get continuity, you see? Similarly, if I do the same right here in the bottom, and I try to measure, I'm going to notice that here also the gap is larger. So if you find the gap larger in the top, it's going to be everywhere else on these lines. So I measure here, there is no continuity. So in order to get it, I have to move my jumper from here to here, and then I'm going to have continuity, you see? So now there is a continuous line. Conclusion. If you keep this in mind, this little thing about you check the gap in the middle everywhere, the horizontal lines everywhere are used to get you access to power. But how can you get access to power? So let's find out. Supposing you only need one voltage, 5 volts, positive, and the ground. And then you do what? You pick up 2 wires, and here is the only place I'm going to kindly suggest you to use a kind of color code. For the ground, you're going to use a kind of dark color, preferably black or blue. Okay? And you put it anywhere. You put this wire from here anywhere on the blue line, and you pick up another one from here, from the red. By the way, red is a standard color for the plus 5 volt, and yellow is a standard color they use for 12 if you need. So you can place it anywhere you need on the red line. Okay, it's not red, this is a kind of orange, but it's close enough to red. Okay, so then here is the place I'm going to come with my 5 volt supply. Okay, so if I'm bringing my crocodile right here and here, and I'm going to give it power, I should be able to measure over here the voltage coming on my lines. So let's do it. I'm going to place a kind of orange wire here instead of red, and here a black one or blue. I'm going to put this on voltage, and I'm going to measure now the voltage between this wire and this one. Okay, so this one now, if I give it enough voltage, I should get a voltage here. Okay, so a voltage is coming here, meaning that I transfer the voltage between the crocodiles to the lines. And if I want to have access everywhere, I have to put jumpers. So if I pick up a jumper from here to here, I relate all the blue lines from top to bottom, like this. So this way, I'm going to pick up from here to here. Now I can have access everywhere on the horizontal blue lines to the negative coming from here. Okay? So I'm going to get access. I'm going to do the same with the red, or my orange in my case. So I'm going to connect orange wires everywhere, like this, and one more, like this. So then I have from the red contact, from the red outlet, I'm going to have access on all the red lines everywhere. I'm going to get access for my circuit to the positive voltage. So that's how you use this kind of power supply horizontal lines. But where are your components? Your components are going to be plugged everywhere else. But the rest of the breadboard, excepting for the horizontal lines, the rest of the breadboard is organized also in groups of 5, exactly like here, but on the vertical, each group of 5, all the holes are related together. Okay? In other words, if I pick up this column here, this hole, that one, and that one, and the last here, all the 5 of them are inside the breadboard related together. How do I know that? Let's go back on the ohms, okay? And if we do, okay, we're gonna find out right away by connecting one wire here in the top and another one here in the bottom, you see? So the 5 holes right here, if they are related together, I should find here continuity. You see? It's continuity between them. So all of them are related together. So each group of 5 everywhere are related together. How am I going to plug my components then? So here I have, let me see, I prepared some parts, okay? Simplest one you may have is a resistor. The resistor has 2 legs. So anywhere I have room, I'm going to plug that resistor. And from that resistor, I'm going to pick up a wire from the same vertical column, and I'm going to plug this wire anywhere I need according to my diagram. Obviously, if I plug this wire here, I have no contact to any of the 2 legs of the resistor. Okay? So I have to be on the column where one leg of the resistor is already connected. Okay? But what if I connect the resistor? By the way, this resistor, if you take a look at the colors, this is 330, meaning 330 ohm. Okay? So if the battery of my meter is okay, I should be able to measure here 330 ohms, you see? Very close. Now, if I connect that resistor here, and of course, if I measure between the 2 legs, I'm going to find the value 330. But what if I connect the resistor like this? This is a wrong connection, because instead of having a resistor here of 330 ohms, you have 0 ohms. You measure between the 2, you just have continuity, see? So what you see here, the value remaining, is only the resistance of my 2 leads I'm using to measure, if there are any. So here the resistor is shorted. There's not a good position to put a resistor on a breadboard. This is one of the things you have to know, okay? Another one. I have here 2 capacitors. Now, one thing you may not have realized yet, why the engineers designed such a thing like a breadboard is because in a way or another, it's saving a lot of wiring actually when we prepare a diagram. For instance, if I plug that capacitor over here, okay, and I have another one over here, and I plug it like that, the 2 capacitors now are in parallel. So I just doubled the initial capacitance of one if the 2 of them are equal value. Now I have the double of the value because if you can remember, capacitors connected in parallel, they add up, exactly like the resistors in series. So how can you put 2 capacitors in parallel and to increase the value? By arranging them exactly like this. So I didn't need any wire for that. Why? Because the wiring is already made inside the breadboard. Another example. I have here what's the most important integrated circuits. The integrated circuits have to be placed on such a breadboard only along that slot right here in the middle. Because if you take a look on the screen again, the top 5 holes anywhere you take them are not related to the 5 holes in the bottom here. So they are insulated, they are separated by that slot, okay? So along that slot, you have to align your integrated circuit. So my good advice for beginners at least is, if you know where the notch is, in that case is on the left side, align all the integrated circuits you have to place with the notch in the same direction to prevent confusion, okay? So now I'm placing it somewhere here, okay? So being aligned along the slot, the top terminals and the bottom ones are not touching each other, are separated from each other. So this is the normal position of any integrated circuit. But I'm picking now a second integrated circuit, and I'm gonna place it right here. You can see that if I do this, it's fitting the integrated circuit, it's entering. But right now, what's very wrong about it is because this one here, if you take a look at it, it has 7 pins on each side, so a total of 14 terminals. So there's the terminal 1, and this is the terminal 14. And you have 0 ohms between them. So they are right shorted, okay? No good. Because usually the pin 14 may be the positive voltage, and the pin 1 may be a signal or an output, I don't know. So right now you just shorted the pin 14 with 1. And if I move it over here, we just shorted the pin 13 with 2. You see, it's shorted. And the pin 3 with 12, okay? And so on. And the last one, the pin 7 with 8, they are shorted. No good. Never do such a thing, okay? Because if you do, you just wasted your time and your circuit won't work. It's guaranteed it won't work, okay? Another example. Another good example is with a 7-segment display we're going to use very soon, okay? So how am I going to use it? As you can see, there are 2 rows of terminals here. So for this one, you're going to put in any position across the slot in such a way that the top terminals and the bottom ones are not touching each other. But take a look at a very wrong connection here. The breadboard is not preventing me to do so. You see here it's fitting, but the 5 terminals in the top are now shorted together because they are on 5 contacts right here, which are related together on the horizontal of the power line. No good. This is very wrong. So never do such a thing. Never place a digit in such a position, even if physically it's fitting, okay? Or similarly, if you do this, you related the bottom line, which is a ground or a -5, to somewhere else on your breadboard. The same wrong connection. So these components, which are semiconductors, regardless if they are simply diodes or 7-segment displays like this one, or integrated circuits, or even transistors, don't place them on the power rails. And last example I'm giving you here is going to be with the power transistor, this one. This is the biggest kind of transistor you're going to be able to place on a breadboard. Actually, the case, it may be the same for a transistor or for a thyristor or for a triac. It depends on the code. This is a transistor. And if I do this, it's fitting very well, because what I forgot to tell you was that the distance between any 2 columns here everywhere is 0.1 inch, exactly like the distance between 2 terminals of any integrated circuit, 2 terminals of a 7-segment display, or in that situation, 2 terminals of a transistor, okay? So this is why they fit so well. But the breadboard does not prevent me from doing this. But if I do so, the base, which is now in the top, for this kind of transistor, if I hold it like this, I have the base, collector in the middle, and emitter on the right side, okay? So, if I do so, now all the 3 terminals are shorted. Your transistor is useless. So it doesn't worth the effort to place a transistor like this, because it doesn't do anything. It's simply shorted, okay? So, with these kind of things in mind, now you have to buy or to order the proper breadboard. They are very cheap, actually. You know, with $10 you can have a breadboard, okay? The smaller format, a bit more for this one having the double, and it's very easy to fill them with parts. Take a look. It doesn't take long before such a board, which is practically identical with this one, okay? before it's going to be filled with components and wiring, okay? So then you may need another one. I'm going to show you. And it's very easy to fill them like this, to fill them with components, okay? And wiring. These are just waiting to be transferred on a prototyping board with soldering, okay? They are just waiting their turn. And until then, they stay here to check the functioning of the diagram, but it's very easy. And these one, they are actually not identical, but very similar. They contain 3 sections. So you can have one section, like this one over here, one section. You can have 2 sections like this one. You can have 3 sections. You can relate them even together. And if I relate them together, I'm gonna make a kind of breadboard of 6 sections. So it only depends on what? On the size of the circuit you need to wire, that's all. But if I can afford to give you an advice, for beginners, maybe the best compromise to start with is this one. Because this one, you can usually put the controls on one side, on one section, and you can put the actual diagram on the other one. So you can do a lot of things with this kind of board. And by the way, just a short reminder, this is a standard full section, 840 holes approximately, because this one has 840, this one has 830, like this. And the double one, exactly like this one, contains a total of 1660 holes, out of which each section has 200 holes, 100 for positive, 100 for negative. You have to remove when you make your circuit. So for this one, the actual useful circuit per section, useful area with holes to do your actual wiring before you connect the power is 630 holes, okay? 630 plus 2 times 50 for the red is 100, 2 times 50 for the blue is another 100. So 630 plus 200 is 830. So useful area, 630 holes times 2, okay, which is 1260 holes available for your actual wiring. And I was showing you how to connect the components. At one point, I'm gonna give you a reminder of that, okay? But at this moment here, I think the subject is pretty well covered. You know how to connect components on a breadboard. So far, so good. So next time, for the next 2 times actually, I have 2 projects prepared to do what? To effectively use these kind of breadboards. So after these 2 projects, none of you can say, I don't know how to use it. Thank you very much for today. See you next time. Bye-bye.